in Amazon, India. I'll oblige Rajiv and keep this really short because I think his contributions and his profile is quite high. So he's got over 50 patents and more than 125 research articles and papers. Rajiv has a bachelor's degree from IIT Bombay and a PhD from UT Austin. And I think we are going to be quite enlightened by what you've got to say, Rajiv. Oh, yeah.
Yeah, thank you for that introduction. So what I'm going to do today is talk about machine learning modeling best practices that we've learned about over the past few years as a result of developing and deploying machine learning solutions. And I will cover 10 modeling best practices in this talk. So let's get started. The first best practice is is really around optimizing directly for economic value as opposed to ML metrics such as precision and recall. So we have seen customers complaining about damaged products and excessive product packaging at Amazon. And this is not only wasteful and bad for the environment, but it also leads to an increase in packaging and concessions cost for us. Now, this slide here shows the different types of packaging arranged in increasing order of cost. So if the packaging types on the right, such as corrugated boxes, are more more expensive, but they lead to fewer damages and lower concessions. So there is a trade-off here between packaging costs and concessions. Now, earlier we were using rules to select the packaging type for a product based on primarily the product category. And now we've switched to an economic value-based approach. And let me explain what that is. So we use ML to predict damage probabilities for a product given the packaging type. And these damage probabilities are then used to select the optimal package type for each product that minimizes the total cost of packaging and concessions paid to damaged shipments. So this term here is the probability of damage times the concessions amount. So this is essentially the expected concessions cost due to damage. So our ML-based approach essentially reduces concessions cost by selecting a robust packaging type like corrugated box for products that are more susceptible to damage, and conversely for products that are less prone to damage, it selects an inexpensive packaging type like polybag, and thus reducing packaging material costs, right? Now, we are using actual cost estimates to select the packaging type for a product. So we need to ensure that these probability estimates are well calibrated. And you can do this using techniques such as isotonic regression or flat scaling and so on. Now, Amazon is a company, at Amazon we focus on the long term. So our ML solutions should also optimize for long-term economic value. So what do I mean by this? Now, actions have a long-term impact. They have a downstream impact. A product purchase can lead to more purchases, thus resulting in an increase in profit. Similarly, on the other hand, if you looked at a product damage, a damaged product may cause customers to shop less on Amazon or even stop shopping on Amazon altogether. And this can lead to a reduction in profit. So we want to estimate the downstream impact of an action. And this action can be a purchase or a damaged product. And we do this by creating two sets with very similar data distributions. The first set, a treatment set, is the customers who have taken the action. And the second set is a control set, which is matching customers who haven't taken the action. And now here the matching between customers in the treatment and control sets are done using customer features like the purchase history, tenure, demographics like age, gender, and location, and so on, right? And the downstream impact of the action now is the difference in 1 year profit between treatment and control. By the way, the Nobel Prize winners for this year's in economics this year got the Nobel Prize for causal inference and causal analysis. So this is essentially estimating things like downstream impact and so on. And so we use this quite a bit at Amazon. So in the packaging equation, we had this term concessions amount, which captures the short-term costs due to product damage. Now to that, we add DSI damage, this term, to even capture the downstream impact of damage on future customer purchases, right? Yeah. So, so the downstream impact here is the difference in the 1-year profit between treatment and control. And so the DSI damage is the term that we add in the packaging equation that I showed earlier. Concessions amount was the short-term costs due to damage, and then DSI damage is called, the term DSI damage is capturing the downstream impact of damage on future customer packages. So essentially, DSI damage is the long-term reduction in profit due to damage. Now, the third best practice is really around generating uncertainty estimates. Now, product weight data is a critical input to multiple things at Amazon: fulfillment fees, calculation for sellers, determining the packaging type for a product, and so on. And these measurements are often erroneous because of errors in online measurements or sellers entering inaccurate values while listing products and so on. Now, the business objective that we have is to predict product weights with error less than X%. So X is some number here. And the approach we took is to train light GBM models with quantile loss to predict the different percentile weight values. Now, one option here is to predict, use this light GBM model that we trained to predict weights for all products, right? This gives us 100% coverage, but the MAPE is kind of high. It's X plus 12%. And that really doesn't satisfy the business requirement. Now, another strategy, an alternative strategy here, is to predict weights only for products for whom the difference between the 95th percentile and the 5th percentile weight is at most 3.3 times the 50th percentile weight, right? And what happens here is that the MAPE drops 1,500 bips from X plus 12% to X minus 3%. And now the MAPE satisfies the business requirement because it's below X%. Of course, what we've lost here is coverage. So we are predicting weights only for 83% of the products as opposed to 100% of the products, right? So by suppressing predictions for products whose predictions have a high variance, we're able to reduce MAPE to below X%, right? So in general, it's a good practice to generate probability distributions as opposed to point estimates. And there are several techniques out there to generate probability distributions. You can use quantile loss, as we've done in this application, but then you can also use dropout in neural networks to generate samples. So dropout essentially zeroes out the output of neurons with a certain probability. Unfortunately, computing the exact posteriors is intractable for all but the simplest models. So, for Bayesian linear regression, for example, you can compute the exact posterior in closed form. Address geocodes is another area that, we work on because addresses are important when you want to ship packages. And address geocodes help to locate addresses on maps. And they also help to plan efficient routes for deliveries, right? And our approach for computing address geocodes is to, leverage all the geocodes for addresses to which we have successfully delivered packages in the past. Now, for each address token, we compute the geocode by taking the mean of geocodes for addresses that contain that token. And we also compute the error radius, or which is the variance of geocodes for addresses that contain the token, right? And here you can see, if you look at address tokens for localities like Marathali, the error radius or variance is much higher, which is at 620 meters, compared to the error radius for address tokens that correspond to building names. So, for example, Purva Fountain Square, which has an error radius of or variance of only 82 meters, right? Now, for a new input address that may come, we can compute the address geocodes by taking a weighted average of the geocodes for the different address tokens, right? And the weight for each address token here is inversely proportional to the error radius of the address token. So in this equation shown here, you can see that the mu's here are the geocodes for the different address tokens that we had computed, and sigma square are the error radius or variance for those geocodes. And this equation, the second equation here, shows the computation of the error radius of the geocode for the address, right? So we are able to generate both the geocode for the address as well as the error radius or the variance for the address. And here again, the variance helps us because we can ignore those addresses whose geocodes have a very high variance. Now, a fourth best practice is to balance both exploration and exploitation. So what do I mean by this? Now, in the packaging scenario, we may not have accurate estimates for damage probabilities, right? This could be due to insufficient training data. It could be for other reasons. For example, there could be a data distribution change, or there may be new package types or new products and so on, right? Now, most ML models out there return point estimates for P damage, which is probability of damage, which corresponds to the mean, okay? But in reality, what you have is a probability distribution over damage probability, something like what is shown out here in the figure here, right? And the point estimate essentially corresponds to P mean, which is shown again in the slide here. Now, the problem is that the probability distribution over damage probability can have a high variance, right? And this makes it a problem when you're using the point estimate P mean to select the packaging type for a product. So for example, if the true damage probability is less than P mean, so it's on the left-hand side, then P mean will end up overestimating the damage probability and use excessive packaging. On the other hand, if your true damage probability is much larger than P mean, then P mean will end up underestimating damage probability and then use too little packaging. So the question here is, how do you select the package type for a product when you have a probability distribution over damage probability? And the approach that we use is based on Thompson sampling, which is an exploit technique. What Thompson sampling does is it draws a sample from the posterior distribution of the damage probability for every packaging type, and then it selects the packaging type that minimizes the cost of both packaging as well as concessions, right? So essentially what Thompson sampling is doing is that it's selecting a packaging type that either has a low damage probability, and that corresponds to exploitation, or it selects a packaging type whose variance is really high, and that corresponds to exploration, right? And what your exploration is doing is it's generating training examples that help to reduce the variance of the damage probability for the packaging type. So as you keep exploring, you're generating more training examples, and that in turn is helping drive down the variance of the damage probability, right? The fifth best practice is around explanations. Now, fulfilling an order involves multiple different entities. You have customers, you have sellers, you have delivery agents. Now, so any of these entities may be responsible when an item goes missing. So for example, and this happens quite often, if a customer complains that they've received a bar of soap instead of a smartphone, then it is possible that the delivery associate switched the product, or the seller shipped the bar of soap instead of the smartphone, or the customer could be lying and falsely claiming that he or she received a bar of soap instead of the phone. So this is a big problem for us. Do we refund the money, or what do we do in these circumstances, right? So the problem is to try and pinpoint the entity that's responsible for the missing item. And here we use attention weights to pinpoint the entity that's responsible for the missing item. And the way it works is we take the customer, seller, and the delivery associate features and feed them into a neural network. And attention weights are computed for each entity by applying a transformation function f to the hidden state for the entity, as shown in the equation out here. And the final probability of the item going missing, which is this y here, is obtained by applying the sigmoid function to the sum of hidden states for the different entities, weighted by the attention weights, right? So this is your final probability. Now, the attention weight for each entity captures the likelihood that it is responsible for the missing item. Okay, so the attention weights at some level are giving some sort of attribution or explanation of why this particular order ended up going missing, right? And so entities who are responsible for the missing item will end up with high attention weights, while entities who are not responsible for the missing item will end up having low attention rates. And this is how we can end up pinpointing the entity that's responsible for the missing item and take the appropriate action to, that could be something like investigating the entity, for example. Now, for the problem of detecting the entity that's responsible for the missing item, AUC of our attention weights model is 13% higher compared to a sugar index based approach. Here, sugar index for an entity is essentially the fraction of orders involving the entity that result in a missing item, right? So compared to just using sugar indexes to do attribution, using attention weights allows us to identify the entity that's responsible for the missing item with 13% higher accuracy. Now, the Amazon product catalog in India has over 200 million products, and sellers are responsible for populating product metadata on our marketplace. So many of these product listings end up having defects. These poor quality listings, again, erode customer trust. They can hurt conversion sales. They can lead to excessive returns. So, for example, here, this slide here shows defects involving mismatches between product attributes like title and image. So, for example, here, the title says the product. I don't know. Can you see that? The title says that the product is a T-shirt, but the product image shows a bag. Similarly, in the other product here, the title says that the color of the product is blue, but the product image shows a pink dress. So if you were a customer and you ordered this product, you wouldn't know whether you're going to get a blue product or a pink product, right? So most likely you probably, unless you like both blue and pink, you probably won't place the order. So and then there are other problems like in some cases attribute values may be missing. For example, like something like color may be missing for a product in the catalog, and this can hurt search refinement experience. So for example, here, this orange dress gets dropped from the search results when the customer applies a orange yellow color filter. So a customer says, I want to see only orange or yellow dresses. And this particular dress gets dropped because the attribute value is missing in the catalog. So, the fact that this dress is orange, that is missing in the catalog. The sellers just didn't upload that information, right? So that kind of leads to a poor experience for customers. So a key capability to identify and correct these defects is the ability to extract attributes from such as color, material, pattern from product titles and images. So here, you can infer the color from both the title and the image. You can infer the material from the title, and you can infer that the pattern is solid from the product image, right? And we use ML models to extract attribute values from product titles and images, and use these extracted values to backfill missing values in the catalog. So a simple supervised learning approach here is to train deep learning models to predict attribute values. The training data for these models can be manually generated. So using the color attribute as an example, human annotators label thousands of images as red, blue, and so on. And using these label data, we train an image classifier. And, the image classifier predicts the color for a given product image. Now, as shown in the slide, we use an exception as the model architecture for the image classifier. And, it maps the product image to a compact embedding, which is then used for in classification. Now, this supervised learning model has 64.1% recall at 90% precision, right? The problem with this supervised learning approach is manual labeling to create all this training data is expensive, right? So to scale to hundreds of attributes, you want to extract hundreds of attributes from titles and images and so on, we need to eliminate human-generated training labels. So that's the sixth model best practice, which is to reduce the manual effort to generate training labels. So, earlier this year, a technology called CLIP was proposed. This stands for Contrastive Language Image Pre-training. And the goal here is to learn image representations from text and do zero-shot predictions without manually labeled training examples. So the way CLIP works is it jointly trains an image encoder and a text encoder to predict correct pairings of a batch of image text training examples, right? So, and to do this, CLIP learns a multimodal embedding space by jointly training the image encoder and the text encoder to maximize the cosine similarity of text and image embeddings of real pairs in the batch, while minimizing the cosine similarity of embeddings of incorrect pairings, right? So you have some correct pairs, and then you have some incorrect pairs, and then you try to maximize, you make the embeddings of the correct pairs close together by maximizing cosine similarity, and you, incorrect pairs, you make them further away by minimizing the cosine similarity. And so CLIP is pre-trained to predict if an image and a text snippet are paired together in its data set. And now we can actually leverage this. We can reuse this capability to do zero-shot classification, right? And the idea here is for each attribute, you're given the image. Now for each attribute, we use the names of all the attribute values here, blue, green, black, and so on, as the set of potential text pairings for this image, right? And predict the most probable image text pair according to CLIP, right? So in more detail, we first compute the feature embedding of the product image and the feature embedding of the set of possible texts by the respective encoders. And then we predict the attribute value with the maximum cosine similarity of the embeddings, right? So here you can see down here, T3, I1 T3, right? That has a maximum similarity, and we predict that this is a black dress. The thing to keep in mind is this is completely zero shot. There's no training examples. We just take the clip, image encoder and the text encoder, and the image is given, and we are able to predict the color, right? Now, the clip has 47.3% recall at 90% precision, right? And the performance of clip is much worse than supervised learning. And this is because clip is pre-trained on 400 million image text pairs, collected from a variety of publicly available sources on the internet. Specifically, clip is not pre-trained on Amazon data, right? So that's the next step. Since we are using these clip models to predict attribute values for product images, we additionally pre-train clip on, image title pairs, product image title pairs in our Amazon catalog, right? So now, interestingly, pre-trained clip has, the performance improves. Recall at 90% precision goes from 47.3% to 53.4%, right? However, its performance is still worse than the supervised learning models. And this is because the training process maps the entire title and image to the same embedding space without leveraging attribute-specific training labels. And that brings us, to the next step, which is leveraging catalog attribute values. Now, it so happens that a large number of products have attribute values populated in the catalog by sellers, right? And as shown here in the table at the right-hand side of the slide. So we can leverage these attribute values in the catalog to generate training labels for every product, right? So we know the color is black. This has been provided by the sellers. And it's not there for all the products, but it's there for quite a large number of products. And so we can fine-tune the clip image encoder using these catalog labels to predict attribute values, right? And even though the catalog labels are noisy, they're not as accurate as manual annotations, fine-tuning the clip models using catalog labels further improves the precision, the recall at 90% precision from 53.4% to 63.4%. So we get a big jump in the performance by just leveraging all the attribute values that are already there in the catalog. And another best practice is to leverage as many signals as possible. So we want to leverage both text and images. Now, besides product images, we saw that even the product titles contain valuable information about attributes. So if you looked at this product title here, we can conclude from this product title that the color of the dress is black and the material is cotton, right? So instead of just fine-tuning the image encoder, we want to fine-tune both the image encoder as well as the text encoder using catalog labels. So to improve the representation power of these image and text encoder, we add a cross-modality attention module to learn these correlations between text tokens and image regions. For example, black in the title and black regions in the image, right? And the resulting text and image embeddings are then combined to predict attribute values. And this multimodal framework that leverages both title and text further improves recall at 90% precision from 63.4% to 68.87%. And so finally, what we have is multimodal clip with no manual labels, right? We have not leveraged any manual labels, and we are getting a recall at 90% precision that is higher than the supervised learning model, which is trained using manual labels, right? So that shows you the power of all the pre-training and leveraging catalog labels and so on. So we're able to, with very little, actually, this is with no manual intervention, we're able to beat the performance of models with. So again, I think the point here is you can reduce the manual effort to generate training examples by using techniques such as CLIP, pre-training that's done in BERT and so on, right? GPT-3 and so on. Best practice also is to design your loss functions carefully. Now, we have a big ads business. Our sponsored product ads coverage is impacted due to lack of ads, matching ads for search queries. And one way to increase the sponsored products ads coverage is to find semantically related queries and then show matching ads for those queries. So for example, here we reformulate the query geyser to water heater and then show water heater ads. Now geyser and water heater are semantically related, and then we show water heater ads for the query geyser, right? Similarly, we can reformulate chappals to slipper or purse for men to men's wallet, right? And that you can see that these are semantically related, but if you look at actual text keywords in these queries, they may not have overlapping text keywords, right? So we use deep neural networks here to learn these semantic embeddings for queries and products, leveraging both product clicks and purchases, right? And the queries and the products are input into the neural network to learn these embeddings, EQ and EP, shown in the slide here. Now there is a natural ordering between purchases, clicks, and impressions. So purchases imply higher similarity between query product pairs compared to clicks, and clicks imply higher similarity between query product pairs compared to impressions, right? So here we have a loss function that takes into account this ordering, right? So for example, for query product pairs that result in purchases, which is this first term here, the loss function ensures that the cosine similarity between embeddings is greater than theta p, right? The cosine similarity between embeddings here is y in the equation. And if you look at the first term at the top, it is minimized with a value of 0 when y is greater than theta p, right? So similarly, this loss function ensures that for query product pairs that result in clicks, the cosine similarity between embeddings is greater than theta c, where theta c is a threshold which is slightly less than theta p. And for impressions, which is the bottom term here, it ensures that, again, the cosine similarity is less than theta c. So it pushes the similarity below in the semantic matching, right? And now we use query pairs with similar embeddings to reformulate queries. Okay, so the idea here was, the loss function here is designed carefully to look at, this natural ordering between purchases, clicks, and impressions. And another example here of ordering between classes is this problem that we worked on to segment customers into boomers, Gen X, millennials, and Gen Z, right? Now, a simple approach is to treat this as a multi-class classification problem. Input are all these customer features such as the purchase history, the browse patterns, searches, queries that customers have done, and your output class label is a boomer or a Gen X and so on, right? But a key observation here is that there is, again, an ordering between classes. Boomers are older than Gen X and who are older than millennials. So this is an ordinal regression problem, right? And, we introduce these new thresholds, beta 1, beta 2, beta 3, and then we require the scores for boomer to be greater than beta 1, and, scores for Gen X to be between beta 2 and beta 1. And all these threshold values can actually be learned, right? So we can reduce the ordinal, we can reduce this ordinal regression problem to a binary classification problem. So, each of these training examples have these additional features in yellow corresponding to the different threshold values, beta 1, beta 2, and beta 3. And we also have a binary class label with values +1 and -1. And the weights for these new feature values that we have here are the threshold values beta 1, beta 2, beta 3. And these weights can be learned along with the weights for the other features X. Okay, so again, the idea here is, you want to try and take into account structure that you may have over class labels, either purchases, clicks, impressions, or again, in this case, this is an ordinal regression problem with boomers older than Gen X and so on. The ninth best practice was really around handling noise, and that's a reality. I think you're always going to have noise, and this is an interesting application that we're developing. Quality is we have a big grocery business. Quality is an important driver of fruits and vegetable purchases and a critical factor to achieve customer satisfaction. And having humans grade the quality of fruits and vegetables by manually examining each individual piece of produce is clearly not scalable to millions of assessments per day. So we are building a computer vision based grading solution, and this analyzes produce images to detect defects such as cuts, cracks, pressure damage, and so on, for products like tomato and onion and so on. Now, the first model that we trained to detect defects had very low accuracy. And when we dive deep, we found that, these annotations of defects on these tomatoes and onions by human annotators were extremely noisy. Because, these annotators are working 8 hours and they're just sitting and looking at image after image and marking them out. So after a point, I think they just become numb to that task, and it's extremely noisy. In fact, 2 annotators had an agreement of only 20% on the annotated defects, right? So the approach we used, of course, there are a lot of approaches. I'm just going to give a very simple thing here, but that's the reality in many applications, that you're going to have a lot of noise. So, we built a model on the first round of annotations, which were noisy, and then we identified those defects where there were disagreements between human annotators and model predictions. And then we took those defects where there were disagreements for a second round of annotations by human annotators. And we found that, the model trained on the second round of annotations had 5% higher F1 score compared to the first round. And just the final best practices around correcting bias. That's also another, something that is inevitable. And if you go back to the attribute extraction problem that I talked about, extracting attributes from titles and images, we created the training data using attribute values for products that were present in the catalog. Now, these products are most likely going to be from the top brands or the top sellers because they have the resources to populate all these attribute values. So you essentially have a bias in the data where the distribution of products in the training set are very different from the overall distribution of products for which you want to extract attribute values. And the way to correct selection bias is really weight each training example by the inverse of its propensity to be included in the training set. And, you can estimate this probability that the example is in the training set by training a classifier. Input to the classifier can be your product features like title, brand, category, image, and so on. And the target label that you're trying to predict is whether the attribute value for the product is present in the catalog or not, right? So that's what you're trying to predict, and that can give you this probability estimate that you try and then you weigh every example in your training set to kind of remove the bias in the training set. So that's pretty much what I had. So I talked about 10 best practices people should pay attention to, at least we pay attention to at Amazon when we build our ML solutions. So I'm happy to take questions.
Why is this sugar index called sugar index?
The sugar index, that's a good question. I don't know. I have no idea why it's called sugar index, but it's a very common, it's a very popular feature to use. And by the way, one has to be very careful with using these sugar index features because they tend to be like, if you're trying to predict CTR, for example, probability of click. Now you can use historical CTR, which is nothing but a sugar index again, for this customer, for example, right? But the problem is a CTR feature, historical CTR feature, may have a different statistical significance based on the number of impressions that were shown, right, to the user. So, you could have shown 10 impressions and gotten 1 click, or you could have got, and you have a 0.1 CTR, or you could have shown 1,000 impressions and gotten 100 clicks, and you still have a 0.1 CTR. But you definitely, the statistical significance of the second sugar index is much higher, the historical feature. So again, I don't know why it's called sugar index, but we use these as features. They're very, very popular features to be used. But again, I think using these features is also very tricky in ML models because, depending on, the statistical significance and the error bars matter, depending on the number of, all CTRs are not the same, even though the value may be the same, but the confidence with which you can say some, predict a CTR may not be the same.
Rajeev, great talk. Thanks. Wonderful talk. Any thoughts on the pricing? So I'm just switching the gears for a moment. So, you have a plethora of a huge number of products, as you mentioned, right? Million,
right.
200 million, I forgot.
Yeah.
Yeah. How do you arrive at the pricing? Because that's so dynamic, right? How do you really arrive at that number? So do you also compare with your competitors from Flipkart, and there are so many other players now? Are you continuously comparing with the competitors and arrive at an optimal pricing?
You're going to get me in trouble with that question. So
well,
I'm just
at a high level.
I think my lawyers will
Good.
come after me. So I can't really. Pricing is a sensitive topic.
But a high level thought.
But actually, to be honest, there's a lot of stuff there. But what I can talk about is we do use ML for predicting prices also. So for new products, for example, we want to know what to price some new product or a product that your competitors don't carry and things like that. So how do you price products, right? And there are many, many different ways in economics literature on how do you price products. You could look at the cost of different components, RAM costs this much, blah, 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 and then come up with a price based on the cost of different components and so on. Or there could be predictions, find similar products to this, and then see what their prices are, and then predict a price for a product. So there are many different ways of using ML to come up with prices, but that's an important area too.
Yeah. Hi, Raju. Thanks for the talk. Very enlightening. My question is for this clip part, which you discussed, the multi-model. What if the text which is entered is not matching with the color of the image? Like that's the example you gave in the beginning also. It's saying blue color dress, and the dress is black in color, and you're taking as a ground truth and passing through the clip for the joint embedding. Won't the model will get confused?
There's noise always. That is noise. So that, I don't think any training data out there is going to be, with 0% noise. There will be noise. ML models are actually, these algorithms are robust to noise. In fact, some amount of noise is good because it helps. It almost acts like regularization. So it prevents you from overfitting. So to some degree, noise is actually helps your models generalize. So these examples that I gave you are a small fraction of the training data. So they don't necessarily hurt the performance of the models. They may actually help your models generalize better, having noise in the training data. Yeah.
Okay, I have a question about the last best practice that you mentioned, the removal of bias part.
Yeah.
Simple question, what is Amazon's interest in removing the bias? Because if we are biased towards the bigger sellers, in what way is it hurting Amazon's interest?
No, I mean, the thing is, you've got to look at where you use the model, right? It's not about the training part. It's about when you deploy this model, what is the data on which you're going to make predictions, right? So you want to make the training data look as much, the distribution of the training data, you want to make it as much, as close to the distribution of the data that you will have in the test setting or in your production setting where you're making predictions. So the bias towards big sellers in the training data doesn't it hurts us when we deploy the model and when we are looking to make predictions on the smaller sellers, right? So we have to make the distribution of the data in the training set sort of similar to the distribution that we would see of the data in production, right? And you do that by these bias elimination methods, which involve weighting these examples differently, right? If big seller products are coming in a lot more, then you downweight those examples, right? And so inverse of the propensity of the example to make it into the training set.
Yes. So can we assume that the proportion of business that comes out of smaller sellers is very significant?
Yeah, no, I mean, because maybe a lot of the missing values are in the smaller sellers. So that's where we are actually using the model to do backfills, right? So we want these models to work well for those long tail sellers, because that's where the models are being used to backfill the values and where the missing values are.
Thank you.
I think we've got one more person here and then we go online.
Okay. So just a few weeks ago, my 14-year-old daughter ordered a pink yoga mat from Amazon. And a couple of days later, so Rajiv Tara, and then a couple of days later, a pink soft stuffed unicorn, a nice big unicorn arrived. So we were really confused. Both, this was also really pink, and based on and then we went back to the website and checked. It was pink yoga mat. So it wasn't a match between a multimodal kind of an error. Of course, we returned it. We got the pink yoga mat. But curious how how this kind of error happened, and then how do you that data to make sure that these kinds of errors don't happen.
That seems strange. That sometimes you may get a wrong color or something of the same product to get a completely different product. That seems strange. So it could be it's possible that there was a problem in the packaging. By somebody made a mistake, and instead of picking the yoga mat, just picked the wrong product and just put it in. And so it could have. Errors do happen because at the end there are humans who are going around looking at the order and then picking out the product and putting it in the in the bin to pack and so on, right? Somebody, a human could make an error. And we also have a lot of third-party sellers on Amazon. So while we may have a lot of checks and balances, but third parties, so we are a marketplace, so there are a lot of third-party sellers selling. So if they don't have stringent processes to check what's being sent, then these sorts of errors could happen.
Interesting.
So, I mean, a lot of times if we see these errors happen often for some seller, we'll send them an email saying that you need to tighten your processes because you're getting a lot of defects of this kind. Returns, we track metrics like returns for sellers and so on. And then we will, inform certain sellers that their metrics are deteriorating and they may want to, tighten up their processes and so on.
So at least that data gets fed back into your whole process.
Yeah, absolutely. So we monitor those metrics to see. Yeah.
Okay, great, excellent. Really good to see the amount of ML that's going into your whole, process. And my daughter will be really happy. I got a direct answer. Great, thank you.
Right. I'm mindful of the time now. I think you see the first question online flashing on the screen. It's from Rakesh Agrawal. For the first problem that you posed, how do you define and measure long-term satisfaction? How long is long-term?
How do you define and measure long-term satisfaction? So I think that's an awesome question. We do measure downstream impact, and a lot of times that captures, like for example, the example I gave on product damages, for example, we will measure what is the reduction in spends of a customer if they got a damaged product, for example, right? And the typical time horizon is at least a year. We'll look out. Because a lot of times there are a lot of events where you may not see an immediate reaction from customers. For example, another great example is, showing ads. I remember I was at Yahoo, and sometimes, we'd show more ads to customers to increase our short-term revenues, or if things were not hitting the numbers, some team wasn't hitting the numbers, they start showing more ads. And, that can really ruin customer experience. All of a sudden you see, just think a TV channel is not hitting their numbers, and then they start trying to make up their numbers by showing more ads. So what does that do to customer experience? At some point, you're going to lose customers. It may not happen in a month. So if you measure just 1 month, you may not see customers desert you. But if you waited for 6 months or a year, you pretty much may not exist. So we look out for at least a year on what happens when certain events happen. Like, for example, there are a lot of events, we may not deliver the product in 2 days. We promised you as part of Prime that we're going to deliver the product in a day, and we may actually take 5 days to deliver it. So what's the impact of that on customers? Do they sell less, buy less on us? Do they leave us? So there's a lot of different events that we look at and try and estimate what is the long-term impact of those events on customer spends.
I think that's pretty much it. So unless there are further questions, and being mindful of time, I think we can call it a day. Thanks a lot, Rajeev.
Okay.
Fantastic
Thank you.
presentation. Thanks.